5-1 notes for Calculus 1. From here on out, we're going to be concentrating mostly on integration and the concept of area under a curve, and whatever it takes to compute that said area under a curve. This will also leak into Calculus 2 for several sections, where you'll be talking about integration and all that good stuff. So basically, what do you mean? What am I meaning by area under curve? So if you look at this first curve here, I guess we can call it just f of x. You'll see that we can actually, from A to B, we can shade the region to the x-axis underneath that curve. And of course, all of this area can be accumulated in some way or counted in terms of what we need. And this turns out to be an extremely important concept when it comes to advanced mathematics. So our focus in this section is going to be about how to approximate that area. Future sections will concentrate on finding that exact area. For now, we're just going to approximate it in terms of our focus. So basically, one of the most popular methods for attempting to approximate that area is to fill the space with rectangles or multiple rectangles. So if you look at our first picture here, after this, we have the same curve, right? Same exact curve, f of x. But what we did was we filled the curve with rectangles instead. Well, what is the benefit of using a rectangle? Well, a rectangle we know the area of already. If I was to look at this, like, what shape could you come up with that would allow us to approximate this? I challenge you to find that shape because it's just not existent. So rectangles we know a lot about, and we can try to find that area. But here, if you look at the way this is set up, it appears that most of the area is indeed shaded underneath this, but it looks like there's some missing area, right? So if you look in here and here, it seems like there's some missing area. Now note, there is also, though, some extra area that is in here, right? But does it really compensate for the missing area that's here and here? No. So if I were to ask you, is this rectangular method going to under or overestimate the area? Hopefully you would say that it's almost certainly going to underestimate the area from A to B. Well, that doesn't mean that the rectangular method is wrong or won't work. It just means there's more to come. There's more to enhance the method for doing so. What about 5 rectangles? So if we move to 5 rectangles under this picture, we get a very different look, so to speak. So if you see now, it looks like the only empty space is right here, but there's a little bit extra here, there's a little bit extra here, there's a little bit extra here, a little bit extra here. So this time, the use of rectangles is actually looking to overestimate the area. So we're getting too much area by doing this, but in terms of logic, which one of these methods do you think is going to be more accurate? Well, hopefully you see that the more rectangles you get will most likely create a more accurate depiction of what the area is. And you can probably picture yourself putting even more rectangles in there and filling up the area a little bit more. Now, there is a one side note here to this. Where the rectangles are placed under the area also is significant to what we do. So I played around with that a little bit to get this underestimate, overestimate stuff happening. But you're going to see in a second what that's all about when we go about doing the area. So what do you need to get out of this first page? Basically that the most common method for estimating the area under a curve is to utilize rectangles, and having more of them is better. Okay, the method for using rectangles to approximate the area under the curve is actually called Riemann sums. So that's going to be a popular calculus word. Basically what we're going to do over the next several pages, and this lesson is pretty long, is we're going to talk about how to use Riemann sums to estimate the area under a curve. But this is not the type of lesson where I can just say, here, see, now do. It's just you need to understand where the formulas come from, or this is not going to mean anything to you. So it's going to be several pages of just breaking down where this all comes from before we can even get to examples. So it's going to be a while before we get there. But going through the derivation goes pretty fast. You just have to do your best to stay with me as we go. Okay, so where we're going to start is the area of those rectangles, as they say. It says, recall the area of a rectangle is computed using area equals base times height. Let's first start by finding the length of the base, denoted change of x. Okay, so they're saying that this is called change of x, as is this, and ... this way, right? All the individual rectangles. Now, remember, these rectangles are all the same length of this, or the base. Wrong way to say that. Okay, a good place to start would be where the area of the rectangles. And recall, the area of a rectangle is just going to be area equals base times height. So what they basically, I want to point out is we need to find the length of the base. So what do we represent as the base? We call that the change of x. So that means all of these are called the change of x, and they're all the same base in terms of length. So just because it's equally divided rectangles, right? So we need to find what that is. So just for argument's sake, so we have 5 rectangles here that are spanning from A to B. Now A and B can be any numbers. So what formula could we use really quickly to find the length of each one of those bases? Well, if this had been, let's say, 8 and this had been 20, then what would you do? You would do 20 minus 8, and then you would divide by how many rectangles you are, right? So let's get rid of the numbers and just write that in. It's going to be B minus A divided by the 5 rectangles. But this is only a formula for this example, right? What if we had a different number of rectangles? We need a more generic value here to represent the true formula. Normally in a problem, we represent the rectangles by the variable n. So we say there is n rectangles. So it makes sense that we're going to replace the 5 with n. So our formula for the length of the base is going to be the change of x is equal to b minus a over n. So again, you can see the diagram here. Each one is the change of x. B and a are the 2 endpoints of the area that you actually want to find. So that's formula we're going to use. So let's use that formula real quick. So let's say that we have 8 rectangles on the interval 3 to 1. How would we find the change of x? Well, the change of x would be equal to, again, b minus a over n. Well, this is a and this is b. So we would get 3 minus 1 over 8, which is 2/8, which is 1/4, which in this section, we're not going to be dealing really with fractions. This is a purely, mostly decimal approximation thing. So basically, we would want to know that the change of x is 0.25, which is going to be the length of every base of the rectangle. Okay, what about the next one? What if we have 12 rectangles? Well, what's that going to be? That's going to be b, 20, minus a, which is a negative 8, over 12. So we'd end up with 28/12, which reduces to 7/3. And we can make it sort of a quick division of that and get about 2.33. Now, this is an example where we might use this fraction just because we don't want a lot of error by rounding this decimal. So worth noting, we probably would use the fraction there in this example. But the key is understanding that we're trying to find the area of each one of these rectangles right here, right? So, and all we need to do is, base times height, right? So right now, look what we have. We already have the base. So we're going to have to basically segue into finding that height. Okay, so moving through this. So again, the height. That is what our goal is here. We're going to have to wait a little bit. We have to go through some concepts first before finding that height, because there's some things that depends on. But before we get there, basically we need some labels and some concepts. So first things first. So what we do is we call them partitions. So each one of these rectangles basically is split up into partitions, right? And each one of these partitions is represented by a variable of x. So the first one is always called x0, x sub 0. Then it's x sub 1, ... until you get to your last value. And this one happens to be x sub 5. So we also, by the way, refer to our first value, as we've stated before, as a, and our last value is b, the endpoints of our area. But these variables x are used and are called very famously grid points. So I'll be using the term grid points to represent these variables of x as we go. So another thing, there's actually, believe it or not, there are 3 types of Riemann sums: left, right, and midpoint. So before we can tackle heights, we actually have to determine what the difference between a left, right, and midpoint Riemann sum. Alright, so we're going to start with a right Riemann sum. That's going to be the key. So what is a right Riemann sum? So it says, notice that the heights of all the rectangles in this diagram intersect the curve on the right side of the rectangles. Okay, so let's use a loud color here. So we'll look here, 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 and here. So does everybody see that the curve intersects the rectangles at the one point in the upper right corner of the rectangle? So that is absolutely dead set called a right Riemann sum. Okay, so you'll get more out of this when we do the next one. So what about a left Riemann sum? Well, it makes sense that the rectangles will only intersect in the left side of the curve, or for the rectangular region. So you can see, look real quick, something very interesting is happening. So basically these rectangles always go right up to the curve on that side, basically, and then the other side of the curve is just sort of floating, right? The other side of the curves, they're just sort of floating here, and they don't really have a real purpose. So, by the way, this is one of the reasons why in the beginning I sort of manipulated this so that we had an under-over representation. So like this one would be called the what Riemann sum? Hopefully you say left Riemann sum because it intersects on the left side of the rectangles. What about this guy? This is a right Riemann sum. So that was part of the reason why we had this underestimate, overestimate, a really big difference. I was just playing around with the rectangles so that you could kind of see what was happening with them. But again, that's what's going on with this. So you can decide to use one or the other, or the next one, which is going to be midpoint, but all of them are legitimate. Some are more accurate than others in different scenarios. So let's talk about the midpoint one. So this time, this one is different. This is the first time you've seen this. It appears that the midpoint of the rectangle is where it intersects the curve. So it makes sense that this is called a midpoint Riemann sum in terms of the method for which we would actually be doing. And again, if you look at the difference between these, hopefully you see between overestimate, underestimate, maybe just about right, maybe. I mean, look at this. So you have, what did I do for empty? I did, so you have a little bit of missing here, a little missing here, right? But then look at what you have a little bit extra here, extra here, extra here, extra here. So maybe this particular one might be just about right in terms of the area that we're actually establishing. So it's important in the beginning that you know the difference between the Riemann sums. Alright, so let's get to finding those heights for those rectangles, right? So first things first, just to review from here, which one of these, this is a Riemann sum, but which one is it? Left, right, or midpoint? So look at the diagram. Where are these rectangles intersecting the curve f of x? It appears to be here, 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 and here, which means we're dealing with a right Riemann sum. So what I'm going to do now is I'm going to go through and show you each one of the Riemann sums and how the heights are going to be determined for each one. So it says down here, it says isolating the fifth rectangle. So let's isolate that. Let me get that outlined. So let's isolate this rectangle right here, right? There you go. It says, how would we determine its height? It says it's pretty clear that the height of the fifth rectangle is at the rightmost endpoint of the rectangle. All right, look at this. So if you look at the height happens to be existing at x sub 5, or at the rightmost endpoint. So the question is what would we do with this value in order to find this height? Well, hopefully you understand that all we would do is plug in x sub 5 into our function value. So for example, if this was like 12, what would we do to find this height? Well, we would plug 12 into the function, and we would get the number height that is right there. So that means this would be x sub 5, or in other words, b. Okay, so in a right Riemann sum, we would find the height of the rectangle by plugging in the rightmost endpoint. But isn't that the case for all the other rectangles? Look at this. What if we want to find the height of the fourth rectangle? Wouldn't that be just plugging x sub 4 into f of x? What about here? Plug x sub 3 into f of x. What about here? Plug x sub 2 into x. What about the last triangle? Plug x sub 1 into f of x. And we're going to get all those heights of those rectangles. But the key thing here is, which endpoint don't we ever actually utilize in order to find a height in a right Riemann sum? Well, clearly this guy right here is never being used. So that is the case in any type of 4a. Okay. In any type of right Riemann sum, we never use the left endpoint in order to find a height in that figure. That is a big deal and something that you have to be able to know when you go through this. Now, if you're looking at a left Riemann sum, so remember left, so the points intersect the curve on the rectangles on the left side. What are we looking at again? Isolate the fifth rectangle, right? This guy right here. So isolate that fifth rectangle. Look at this height right here. Look at that height. It's this right here. So which one of the variables, the partition variables, are we plugging in to get that height? We're plugging in x sub 4. I mean, it makes sense, right? X sub 4 is going to be the key one that we're going to do. So f of x sub 4 will get us that figure. So what do we do when we go to the next one? So go to this one. What are we plugging in? X sub 3. This one, x sub 2. This one, x sub 1. This one, our first endpoint. So we are using our first endpoint for this one as we go through it. This is supposed to be up here. So x sub 4. And if we continue with the same logic here and we get all these, again, for a left Riemann sum, which one of these is not being used? It looks like x sub 5 is actually not being used in this problem, which is essentially b, our last endpoint. So far we have a summary basically looking like this. We have, in a right Riemann sum, we ignore the leftmost endpoint when finding heights. In a left Riemann sum, we ignore the rightmost endpoint when computing heights. But the key is we never use all of the partitions, because if there's 5 rectangles, there's 6 partitions. and that doesn't make any sense to use them all. Okay, so what about our midpoint Riemann sum? Okay, a little different scenario for this one. Why? Because now we're dealing with not the right or leftmost sides of the rectangles. We're dealing with the midpoint value of those rectangles, and there being the, the partitions and how they come up. So this can be a little bit tricky for sure, but just realize that it's a pretty, it's very algebraic in nature. So my question is, let's say we again isolated this fifth rectangle right here. Okay, this fifth rectangle, getting sloppy. Okay, we got that, guys. So if we were to look at that, what would be the value of the height? How would we find it? Well, we basically would have to find this value right here of x. Well, for now, just ignore these guys right here. We'll talk about that later. The key is that we need to sort of situate ourselves into what those values would be. Well, we know what these are. They're x4 and x5. So how do we find this value, this point right here? Well, isn't this halfway between? So wouldn't we take x5 plus x4 and divide by 2? We would. So what are we doing? We're taking x4 plus x5 divided by 2, and then we're plugging that into the function to get this height in the problem. So basically what happens is that this is going to be the fact of what you're going to do the whole time, right? So like here's going to be the average of x3 and x4, and you're going to go through the entire diagram. You're never going to use any of the endpoints or basic partitions. You're going to be finding the average of them in order to calculate all of those values. Okay, so in the end, what do we basically need to do? So we just went through these previous several pages, and we talked about first how to find the base. So the base of the figure is the change of x. We figured that out using a formula. And then we determined how to find the height of all the rectangles. And we use a symbolism called f of x star k. So it sounds very galactical, but basically, what is x star k? All it is the value either of the grid point or the midpoint of the grid points. So that's where these guys came in, right here. So that would be x star 1, x star 2. In the other problems, this would be x star 1, x star 2, and so forth all the way through. So all you're doing is plugging those values in. So this is all in formulas right now. So I can't say it's super easy for students to grab upon this unless they have examples. So of course, that's really all we can really do right now is get to examples. I just want to point this out for a second. So if we want to find the area of the rectangles, then basically this is the formula for each area, which means we have to do this calculation for each rectangle. So what we do is we set it up like this. We say, okay, so for the first rectangle, we have to find f of whatever basically the value of the grid point or midpoint is, times the change of base. Then we have to go to the second rectangle. So this is first rectangle. This is second rectangle. So you got to keep on going until you get to the last rectangle, which by the way is the nth rectangle, right? So you go all the way through. Now this symbolism right here is a way to summarize that just in case we end up with 20 rectangles. So we would say, remember this is summation notation here. So this is summation notation. So we would say from 1 to n, the last rectangle, find f of x star k times the sum of x. It's just a shortcut method, but I need to point out something very important for our calculations. So we could do this for every problem, but note, isn't the change of x, didn't we say that the change of x is going to be stagnant? it's never going to change within one problem. So why would we take the same number and multiply by the change of x every time, when instead we can factor it out and just take the sum of all the other individual other terms? So in the end, what you want to do is you want to use this for calculating the Riemann sum of any area that we're trying to find. So calculating the Riemann sum. Okay, so by now, after several pages of technical explanation, your brains might be a little fried. I get that. Some of you might be okay, but the key is now is we really have to, get to some examples to get this going so that you understand what you're doing in these individual problems. I will say, I know this sounds crazy after all that technical jargon we went through, but this is the easiest section by a mile for students. They usually ace this without a problem. Why? Because there's actually no calculus in this section. This is straight algebra and geometry, basically, looking at a picture. So hopefully you get the same experience when we go through this problem. It says for number one, it says, let's say R will be the region. So we'll let this variable be the region bounded by the graph of f of x equals 2x plus 3 and the x-axis on the interval 0 to 2. So basically, what are they saying? So they're saying that we have this region right here, which is we can shade in if we want, right? So we can shade in this region if we want. I'm just doing an estimate here. It doesn't have to be perfect. And we're calling this region R, okay? So what we need to do is we need to go through the process of what the whole Riemann sum is about. Okay, that is our goal. It says first, divide the interval into n equals 4 subintervals. Okay, when I say n equals 4 subintervals, that is analogous to the number of rectangles. So it's going to be the same thing as the number of rectangles. So what do? Remember this formula? The change of x is equal to b minus a over n. So we need our equal length for each one of those rectangles that we end up developing. So what is it going to be? Well, remember a and b right here. So we're going to get 2 minus 0 over 4, which is going to end up being 0.5. So what are we doing? We're taking our full interval, which goes from 0 to 2, and we're splitting it up into 4 intervals of 0.5. So watch. 1, 2, 3, 4 intervals that are all 0.5. Okay, so I purposely marked that on the graph so you see it. So what does that mean the grid points are going to be? Well, those are already marked. So it looks like the grid points for our problem are going to be these guys. So these are going to be the markers that separate all the values that are there. How do I find that? I start at 0, so 0, and then I add 0.5 over and over again until I get to 2. So 0, 0.5, add another 0.5, 1, add another 0.5, 1.5, add another 0.5, 2.0, and we're at the end. Note that there will always be one more grid point than subinterval. Always, well, whenever you do left and Riemann sums at least, so we don't want to go with always. But for these scenarios, there is going to be one more grid point than the interval that you compute. Now, what if we want to approximate the area using a left Riemann sum? Well, let's look at the picture real quick. So remember, it's the same area, but what did we do? We basically took our rectangles and drew them up so that the left side of the rectangles intersect the curve that we want to find the area under. So, based on what you've learned from a left Riemann sum, if you look at these 5 grid points, which one of these are we not going to use to determine the height? Well, hopefully you're already spitting that out at me in your brain there while you're watching this. But if you're not, you can look at the diagram and clearly see that these 4 are being used and this one is not. So whenever you use a left Riemann sum, you ignore the rightmost endpoints. So we're going to be using 0, 0.5, 1.0, and 1.5, and specifically not 2.0. So to be clear, these are not the heights. These are the values of x's we need to use to find the heights. That is the key concept here in terms of finding these. Okay, so the next step is now, since we have the measures of the bases, which is 0.5, and we know where to compute the actual heights, we can go ahead and find the area of each rectangle. So recall, in order to find the area of each rectangle, we use the formula right here. Okay? What do? We basically we plug each one of the partition values, the grid points, into the function. We add them all together, and then we multiply by the change of x. So let's do that. So we're going to do, first we're going to take f of the location of the first height. Well, the location of the first height is going to be at 0. So f of 0. Then we need the location of the second height, which is at 0.5. And then we need the location of, and these are all the heights, by the way. Erase those. F of 1. And these are, and the last height is going to be at f1.5. And remember, we ignored this one. So then we have to multiply by the change of x, which we previously calculated to be 0.5, and that is right here. Okay? Okay, so what about the math here? So remember, what is f of 0? How do we find that? Well, if you look back, we have the equation of this line is f of x equals 2x plus 3, which means all we have to do, and I'll do a little bit of simple math underneath here so that you have it in your notes. You just have to do 2 times 0 plus 3, 2 times 0.5 plus 3, 2 times 1 plus 3, 2 times 1.5 plus 3. Okay, that's all you have to do. And when you do that, you're going to get 3 plus 4 plus 5 plus 6, all multiplied by 0.5, which is 18 times 0.5, which is going to give us 9. So therefore, we are approximating the area under this curve. So remember, the full curve is here, right? The whole curve. So we're approximating this area to be approximately 9 units squared, basically. You don't have to write that, you can just write 9. So, but once we're done here and we have this number being our left Riemann sum, and by the way, I usually abbreviate left Riemann sum as LRS, so if you see that, that's what that means. Just like right Riemann sum is RRS and midpoint Riemann sum is Mrs. MRS. So just so you know. Once we get this number, then we want to make a judgment. So does it appear that the rectangles in this picture are underestimating or overestimating the actual area? Well, if you look at the green that actually developed there, it looks like this is vastly underestimating the area because we have all of this not being taken into account. So what that means is this is left Riemann sum is not the most ideal use for approximating the area, but still very valuable for learning how to find the area. Okay, so what about the same problem with a right Riemann sum? Okay, so again, rectangles are basically nice and up against the right corner of the rectangle. So it is worth peeking at this and how different it looks. So ready? So left Riemann sum, right Riemann sum. So interesting how different they look, right? So it kind of gives you an idea of the different dynamic of what you're doing here. So the first part here just says, what values of x do we use to determine the height? So basically, what are the grid point values that we're going to use? So if you look here where the dots are, it looks like it's going to be these 4, right? And which means that just like with every right Riemann sum, we ignore the first endpoint. So we're going to be using 0.5, 1, 1.5, and 2. And I'm just going to write not 0. Okay. So once we have that, we can quickly go to finding the area because we already did all the other work with the change of x for the left Riemann sum. So we can go right into this. So what's the area going to be? So we got f of, what's our first value? This time it's 0.5. Next one, f of 1. Next one, f of 1.5. Last one, f of 2. Okay, multiplied again by 0.5 because that's the change of x has not changed in the scope of our problem. Okay, it's still the whole same interval. That will change though. It's not always 0.5. It just so happens we haven't left this problem yet. Okay, so again, what do? All you have to do is do 2 times 0.5 plus 3. 2 times 1 plus 3. 2 times 1.5 plus 3. And then for the first time, we're doing 2 times 2 plus 3. Okay, what are we going to get? So we're going to get, we're going to basically start one later. So 4 plus 5 plus 6 plus 7 times 0.5, which is going to give us 22 times 0.5, which is 11. Okay, so last time we got 9 as our approximate area. This time we have 11. Now if you look at the picture, what appears to be going on here? Do we have a severe over or under representation? Hopefully you're saying over, because if you look at this area in here, this is all just adding on to area that doesn't exist. So this is an overestimation. So basically a right Riemann sum wouldn't be great here either. But interestingly enough, if we see a 9 and 11, we probably could guess that the area under that curve is probably going to be 10. It's not always perfectly in between, per se, but in this standpoint, there's a good chance it probably will be when we're all said and done. Okay, so this is when it gets a little bit tricky, midpoint Riemann sum, right? So if you look at the picture, you can clearly see that the rectangles are drawn at the midpoints of each rectangle, right? So we're looking at this guy and thinking, well, these are the case, then where are the heights going to be located at? Well, you could do the math, right? You could do, so like this value here is going to be, hold on. This value here is going to be 0 plus 0.5 over 2, but most of you mentally are just going to say, oh, well, that's a quarter. Just like mentally, you're going to be like, oh, this is 0.75, this is 1.25, this is going to be 1.75. Okay? Which means that our heights are going to be determined at these values only for our problem. Okay? So there you go. So those are our heights. We're all good there. So it's going to be a little different. It's not taking any of the physical grid points themselves, partitions that we marked. The grid points are actually going to be ending up being the midpoints of these values. So moving on to like we did before, we can then do our calculations. What are we going to get? This time area equals, we're going to start with our first value of x, and that is 0.25, and then we're just going to do the same thing. We're going to move through, and we're going to do every other value. And multiply again by 0.5, because that's the change of x that has not changed. Alright, so hopefully by now you're pretty clear that you're doing, 2 times 0.25 plus 3 and so forth. I'm not going to keep doing that. So what do you get as the values? You're going to get decimals. So you're going to get 3.5 plus 4.5 plus 5.5 plus 6.5. And that's going to be multiplied by 0.5 in the end, which is going to be 20 times 0.5, which is indeed going to be 10. Okay, it turns out in this problem that this is an accurate result. So the best method to use for this linear function is to use the midpoint Riemann sum. And what ends up happening, by the way, is that the missing value in here, like in here, right here, ends up perfectly canceling out with the extra area. on each one of these as we go through, right? So this is the accurate area under this curve that we can compute. But that doesn't mean that the midpoint Riemann sum is the all-hail method that we use. It depends on the problem which one might be more accurate in terms of what we're doing. All right, so before we get to another example, let's basically highlight the main calculus concept. Even though in the example problems you're not really doing any calculus per se, there is calculus behind this, because why are you learning, basically? So why are calculus students asked to learn computing area under a curve, specifically using this method? What is the point of that? Watch. So let's say we concentrate just on a right Riemann sum approach, okay? So if we look at this first picture, clearly we have a right Riemann sum. So we're using the same line, 2x plus 3. Note that I have 10 rectangles. Okay, so right now when you look at these 10 rectangles, it seems like we're over the area a bit, right? Not so good. But then what if we went to 25 rectangles? So this is a realistic look at 25 rectangles. Well, there is a tiny bit of area for each one of those 25 rectangles, but overall, if we added those together, it does seem like it's going to be less of an overestimation of what we're actually going to get there. But then look at 100 rectangles. So does everybody see you can barely make out the areas that are above? Which means that this is an incredibly accurate representation of this area as long as we have an extraordinarily large number of rectangles. So let's take this further. Let's look at the example. So remember, we've already done the calculation for 4 rectangles. I believe we got 11, right? So I put that in the diagram here. So in our table. So look at the ones above here, 10, 25, and 100. So we don't need to do the calculations. It's too gratuitous. But I did the calculations. So what do we get? So if we did 10 rectangles, which is this one, we're going to get a right Riemann sum of 10.40. If we do 25 rectangles, we're going to get a right Riemann sum of 10.16. If we do 100 rectangles, we're going to get 10.04. And the picture that isn't even here because you can't even see it is, what if you did 1,000 rectangles? What do you get? 10.004 as the Riemann sum. So note, I used a simulator to do this. So I think you guys might know where this is going, right? What does it appear that this value is actually approaching? Remember that number 10 we talked about that was the midpoint Riemann sum? That is actually the true area underneath this 2x plus 3 curve. So, or line is the best way to put it. So, but what is this? What is this? What are we doing? Oh boy, we all know. The limits. So this entire concept of a Riemann sum is essentially, so by the way, this is the formula for a Riemann sum, right? But then what I did was I plopped on a limit as n goes to infinity. So why is this legitimate? Because remember, k is the number of rectangles. So we would say from one rectangle to the last rectangle. But if I put a limit on there as n goes to infinity, that means we're going to an infinite number of rectangles. And isn't that what is happening here? It's heading towards infinity. So essentially, if I wanted to find the true actual area, not an approximation, but the actual area under that curve, then I would be using this formula to do that. And it turns out in our future sections that this is actually equal to a integration. Okay, that's going to be the big jump that we're going to make very soon, but this is essentially integration. Okay, so this is actually page 22 in your notes. So the last couple semesters, I keep on forgetting to take out this page. That's the summary of the story. So we're not going to do it in practice, because the next page is a little bit more involved. Students have basically said that it's too many examples, it's overkill. So what I'm going to do is I'm just going to give you the answers to each. So if you want to do, let's say, them on your own as practice, you can. But I have 3 examples on the next page that will be more than enough to cover the example requirement for going through these problems. So these are the areas that you should get if you do a midpoint left and right Riemann sum for this function on this interval. So feel free to do it as extra practice, but what we're going to do is we're going to move on to page 23, which has more involved functions and pushes the envelope a little bit more. Okay, so the goal in this problem is to find a midpoint Riemann sum for the function e to the x on the interval 0 to 10. Okay, they also tell you to use n equals 5 subintervals. So every one of these, I would say this is the way that most questions will be asked on an exam or lab situation. So just be comfortable with the wording from where you go from there. Okay, so what is the first step that you always take in any Riemann sum problem? So this is the first one we're doing as one isolated problem from scratch. We were kind of all over the place with A, B's, and C's in the other one. So this is a good way to organize your thoughts. So we always do the change of x first, remember, which is b minus a over n. So if we do so, we're going to get 10 minus 0 over 5, which is going to give us a equal length value of all the bases of 2. Okay, so what we're going to try to do in this problem that is unlike what you've seen is not use a picture. Okay, so normally I have a nice pretty picture over here that you can look at and help yourself out. Well, it's important that you don't have that. You got to be able to do this without it. So that's what we're going to do. So the change of x is 2, the first thing right off the bat. So what does that mean? So that means that our grid points, possible grid points, are going to be located where? So remember, we start at 0 and we add our change of x until we get to our endpoint. So 2, 4, 6, 8, 10. So these are our possible grid points. So if we had a graph, these would be the labels on the graph as we see it, and the rectangles would basically be, I know this kind of looks weird, but they basically would be between them. Okay, that would be the idea. So what does that mean? The heights are at what values? So this is a midpoint Riemann sum, which means the heights have to be at the midpoints of these consecutive numbers. So what is the midpoint of 0 and 2? It's 1. What is the midpoint of 2 and 4? It's 3. Midpoint of 4 and 6, 5, and so forth, until we get to the last midpoint, which is 9. So when you're done, this is a good hint for you. When you're done, you should have the same number as heights as number of rectangles, n equals 5. If you don't, then likely you did something very wrong. Okay, so now what we can do is we can jump right into finding the heights. So how do we do so? So remember, area is equal to f of whatever my first height value is, 1. Then I continue with the sum of all of them as I go through the picture, or the heights and the rectangles. So when I'm done, I should have 5 function values because there are 5 rectangles. I then multiply by the change of x, which is 2 in this problem. So what am I doing? So again, a little bit of short math here. I'm doing e to the 1, e to the 3, e to the 5, e to the 7, e to the 9 for each one of these. As I plug them in, all I'm doing is plugging them into the function. So if I do that, I can basically just put that into the calculator. I mean, I could do e to the 1, blah, blah, blah. I'm just going to give it to you so you have it. So I did these to as many decimal places as I could all the way through. So for each one, not a comma. Hello. How about a plus? And then 148.4132 plus 1,000. We're going to get quick, remember, because you know the concept of growing exponentially. The numbers are going to get ginormous very fast. That's probably not a word, but I like the word. 839 right there. And then we're multiplying that by 2. So when's all said and done, if you do all of this math, you're going to get 18,741.8681. We'll make an approximate sign because obviously we rounded there. So this is the approximate area underneath the curve. Now, what I want to do, though, is I want to add something to this. So this, to be clear, this is the approximate area. So by methods that you will learn later on in calculus, so within the next couple sections, you will learn how to find the actual area under this curve. And I just want to share with you that the actual area is 22,025.4658. Okay, so this right here is the actual area. Now, note, you want to make a note here that this is not part of this problem. So, from future material, right? Let's do computed from. Okay, why did I do that? Because I don't want to confuse you. I just want you to see that that we do have an actual area we can compute later on, and this is just an approximation, and that's what Riemann sums are. So this shorted this area by almost like 3,000 to 4,000 units squared. So just, does that matter? Is this going to have anything to do with exams or labs that you're going to write? No. But I just wanted to show you that that would have been the actual area, so we're a ways off from what actually should have been in this problem. Okay, so next we're doing a left Riemann sum, and this is for root x on the interval 3 to 6 with 4 rectangles. Another word for subintervals for what we're doing. Okay, so again, change of x, right? So change of x is going to be 6 minus 3 over 4, and we're starting to get some not so nice values, right? So 0.75. So if we want to determine where the grid points are located on the graph, then what do? We start at 3, and then we add our change of x each time. So 3.75, add 0.75, get 4.5, add another 0.75, 5.25, add another 6. If for some reason you don't actually come to this exact value, then check your math, because it is most assuredly incorrect with what you did, and then you can find the heights. If this is a left Riemann sum, then we basically have ignored what value. So we always ignore the rightmost value in a left Riemann sum, right? So that means our heights are at 3, 3.75, 4.5, and 5.25. And when you're done, as we stated before, then the values you get here should be the same number as the number of rectangles. Okay, that's a great way to remember how to do it. Okay, so once we have that, we can jump right into finding the area again. So we're taking f of, our first height is at 3, next at 3.75, then 4.5, then finally f of 5.25. Again, there should be 4 function values because there are 4 rectangles, and we're multiplying by 0.75, which is our change of x. Again, what are we doing? So just the mini math of this, root 3, root 3.75, root 4.5, root 5.25. We're just subbing into the function. That's it. Okay, if we do so, we're again going to get some nasty values. So 1.7321, we're going to get 1.9365, 2.1212, 2.213 plus 2.2913. Again, if you want, you can just literally plug the blue numbers in as they are. You don't even have to do the decimals for each one around. It's probably better to put in, so you don't get error, put in the blue values. But I'm putting this out just in case things go astray with your math and you get something different. So if you do this, in the end, you're going to get approximately 6.0609 as the approximate area from this left Riemann sum. And just like before, remember, this is from future calculations that you don't know how to do yet. The actual area is 6.339. So interestingly enough, that is, that's pretty close, right? It's pretty close. We're only like 3/10 off, so it's a pretty good approximation of the actual area that is underneath that curve, root x, from 3 to 6. Okay, so last problem in this section. So you can see why I skipped the previous page, because we're already doing a ton of examples. It was a little overkill that I was doing there. So change of x. So change of x is going to be 3 minus a -1 over our n, which is 6. So that's going to give us basically 4/6, which is 2/3. So since 2/3 is a repeating decimal, we're just going to leave 2/3 as is. So what does that do for us? So our grid points. Okay, this is going to get ugly. So where do we start at? We start at -1. So then what do? We add 2/3 to that. If we add 2/3 to that, we're going to get -1/3 as our next one. If we add another 2/3, we're going to get 1/3. If we add 2/3 to that, we're going to get 1. If we add 2/3 to that, 5/3. And then if we add 2/3 to that, we're going to get 7/3. And then we're going to get, finally, 9/3, which is just 3. Okay, so these are grid points, which means the heights are at, looks like my tablet's getting a little buggy here, just so you know. So it's going to be slow down. I might have to restart after this lesson. It says heights are at what value? So this is a right Riemann sum. So if it's a right Riemann sum, we are ignoring the first grid point. So we're going to get we're going to be doing -1/3, 1/3, 1 5/3. Slowing down, bugging out. 5/3, 7/3, and 3. Okay, so for the area computation, what does that look like? I'm going to move it down a little bit because it's going to be longer. So we're looking at f of our first grid point, which is -1/3, plus f of 1/3 our next, plus f of 1, plus f of 5/3, plus f of 7/3, plus f of 3. And we're going to be multiplying all of that times 2/3, and we'll keep it that way because, again, that's a repeating decimal, so let's keep as much accuracy as we can. Now, the function itself is x squared, so we can actually keep these as fractions all the way. So just as a reminder, so this is -1/3 squared, this is 1/3 squared, this is 1 squared. This is what we're doing all the way this way, right? All the way to find these calculations. So what are we going to get? Well, we can actually square these and make fractions out of them. So this is going to be 1/9. This is 1/9. This is 1. This is 25/9. This is 49/9. And this is just 9. Multiply by 2/3. If you put all of this into your calculator, you're going to get 12.2963 as the approximate area with a right Riemann sum. And just to give you an idea of the actual, which you don't have to calculate, make a note to you somewhere, it's going to be 9.3 repeating. So we're back to not so great of an example of using the right Riemann sum here to find the area. We're like 3 units off, square units off. So this is basically how this works. You might not even need all these examples to get through, but I wanted to make sure to bring in some problems that have fractions and multiple triangle rectangles going all the way, all types, but these are pretty good examples to get you started on the Riemann sum calculation.